Now for section 2.9, LP spaces. And this topic gives us a bunch of examples of Banach spaces, so that's why it's pertinent to us at this stage. So we'll introduce these two types of spaces, big LP and little LP, P being between 1 and infinity, including infinity. We'll define L infinity spaces also. The elements of the capital LP, the big LP, elements of those spaces are functions of a particular type related to measurability and integrability in the sense of Lebesgue. So we're going to have to explore some Lebesgue stuff. The little LP spaces don't require quite so much background. We'll tack those on kind of near the end, in fact, which is often how they're dealt with in a real analysis class. The deep theory lies with the capital LP spaces. So these are examples of Banach spaces, that is, complete normed linear spaces. We'll introduce the norm. We'll claim completeness, but we won't prove it. There's no proofs in the notes for this section. To completely appreciate the development of these ideas, we need an understanding of Lebesgue measure, Lebesgue integration, convergence theorems from a real analysis class. So really, this is many topics from Real Analysis 1. Some of this LP stuff usually is actually done in Real Analysis 2, at least when I do it. This Real Analysis class on Lebesgue integration and Lebesgue measure isn't a formal prerequisite for this class for the fundamentals of functional analysis. So what we're going to do is just skim through these ideas, get the definitions on board, get some central theorems stated, but no proofs. We don't have the equipment to go through the proofs of this. You'll have it once you take Real Analysis 1. All right, there's a link to notes on Real Analysis 1, and I'll insert a whole bunch of links in these notes to the topics from the Real Analysis 1 and Real Analysis 2 classes. So we'll start with a definition of a sigma algebra of sets. Given a set, omega, a collection S of subsets of omega is a sigma algebra if the following hold. So you're going to think of these followings as closures of the collection of sets S under various operations. Part A says, given any finite or countably infinite sequence, A1, A2, and so forth, of sets in S, we have first, the union of those sets is in S, and the intersection of those sets is in S. In a closure terminology, we'd say collection of sets S is closed under finite and countable unions and is closed under finite and countable intersections. Actually, when you say countable, that usually is understood to include finite. Part B, for any A in set S, the complement of A complement, is also an element of S. Complement with respect to the set under which we're having the conversation, capital omega. So omega set minus A is what we mean by A complement in this setting. And so a sigma algebra is closed under complements of sets as well. And finally, omega itself is required to be in S. Hey, if the whole set omega is an element of S, looking at complements, it must be the empty set is also an element of S. So a sigma algebra is a collection of subsets of a given set that's closed under countable unions, countable intersections, complements, and it contains that whole set. There's some redundance in this, as you might be familiar with. From De Morgan's laws, we can take closure with respect to unions and this property about complements and deduce closure with respect to intersections, countable unions and countable intersections. And vice versa, we can take closure under countable intersections and complements and use De Morgan to deduce closure under countable unions as well. So we don't need both of these in part A. Both hold this is fine, but there is some redundance there. It's consistent, so we don't have a concern with that. Some examples of sigma algebras. If we take S to be the set, and the power set is a sigma algebra on, say, set S. We're using S instead of omega here. But a power set of a given set includes all of the subsets. Well, then that's closed under unions and intersections and complements because it's all of the subsets of the given set. So we'd have an example of a sigma algebra on a set there. A more interesting example of a sigma algebra on this set R, just where we'll use this exclusively, or at least almost exclusively. We'll be considering subsets of the real numbers and Lebesgue measures and Lebesgue integration as relates to that set, those sets of real numbers. But a sigma algebra on the set of the reals of interest is the smallest sigma algebra containing all open sets of real numbers. We'll denote it with a calligraphy B. These are called the Borel sets. So I dare you to think of a set of real numbers that's not a Borel set. It includes all open sets. Okay, then it includes all closed sets because it's closed under complements. It's closed under countable intersections and countable unions. If it includes all open sets, it includes all countable intersections of open sets, which is a new class of set and an example of a Borel set. Countable intersection of open sets certainly may not be open. A countable union, an arbitrary union of open sets is open, but a countable intersection of open sets may not be open, may not be closed either. Maybe something more exotic. It's an example of a specific type of Borel sets. Though I dare you to come up with an example of a set that's not a Borel set, there's lots of such examples. In some sense, the Borel sets aren't a big collection of sets. There's not many Borel sets in a cardinality sense. The cardinality of the real numbers is the same as the cardinality of the Borel sets. But if we go considering how many subsets of the real numbers are there, what's the cardinality of the power set of the reals, that is, well, that's strictly greater than the cardinality of the reals, and so strictly greater than the cardinality of the Borel sets. In other words, there's a whole bunch more subsets of the reals than there are Borel sets of real numbers. There's a link to some notes there that discusses Borel sets and cardinalities. A measure, mu, on a sigma algebra S is a function from S to 0 to infinity. Notice the infinity symbols being included here. So sets with infinite measure are on the table. And we're requiring this mu thing, this mu measure, to be countably additive. That is, when we take a countable collection, A1, A2, and so forth, of disjoint sets, then we have the measure of the disjoint union equals the sum of the measures, sneaking in this little symbol, union symbol with a dot inside it. That's a commonly used symbol to indicate that we're dealing with a disjoint union. Maybe you've seen this before. If so, probably in analysis. This is a reasonable place to introduce it because, of course, we need this disjointness to get the equality. The measure of the parts equals the sum of the measures because the parts are disjoint. If they weren't disjoint, I wouldn't expect necessarily to get this equality. But let's introduce that symbol. We'll use it sporadically. It plays a big role when you're dealing with measure theory, and we're touching on measure theory, so we'll use it now and then. So countable additivity is required, and we're requiring the measure of the empty set to be 0. So measure defined on a sigma algebra, and the measure of a disjoint union is the sum of the measures, countable additivity, measure of an empty set is 0. So that's not much structure just yet. We'll require more structure when we look at things a little bit more detailed in terms of Lebesgue measure. Given a set capital omega, collection of subsets S, and a measure mu, this triple of items is called a measure space if S is a sigma algebra of subsets of omega and mu is a measure on S. So when the sets on which the measure is defined is a sigma algebra, that's when you get a measure space by definition. A function f mapping set omega into the reals is called a measurable function if for all real numbers r, the inverse image of the interval from -infinity to r, including r, is an element of S. In other words, is a set on which mu is defined, is a measurable set. So this is very geometric. We're taking inverse images. Of course, this doesn't imply that function is invertible. It's an inverse image under that function. It's all the input values that give an output value from the function of at most lowercase r. You're requiring these to be measurable for reasons which are well motivated if we dig deeply into measurable functions. And we won't dig too deeply into measurable functions. Well, this will pop up in passing, and I'll try to give some inspiration as to why you would want to consider such functions. It's so you can do integration, is the short answer. Okay, as stated, we'll omit the details about Lebesgue measure, but suffice it to say, so we're making some claims here. A Lebesgue measure, which we'll denote with an M, is defined on a sigma algebra of sets of real numbers. We'll denote calligraphy M. It's called a sigma algebra of Lebesgue measurable sets. For every interval, every interval is in that sigma algebra. That means M contains all open sets and all closed sets, because you know what an open set of real numbers looks like. It's a countable disjoint union of open intervals. Big result from senior level analysis, an ability to classify open sets in terms of open intervals. One more time, an open set of real numbers is a countable disjoint union of open intervals. Well, if you believe that every interval is in calligraphy M, remember calligraphy M is closed under countable unions, then the countable union of, say, open intervals is also in M. And so all open sets are in M, and if that's the case, M is closed under complements, then all closed sets of real numbers are also in M. Thus the claim that M contains all open and closed sets. I don't think this is commented in the notes, but it turns out M contains all the Borel sets as well, and that's kind of why they're introduced. The Lebesgue measure of an interval is its length, a property that would have to be proved, though we'd need a formal definition of Lebesgue measure. We're kind of glossing over some of that. Got some links to some of these ideas in the notes. In terms of cardinality, the cardinality of the collection calligraphy M of Lebesgue measurable sets equals the cardinality of the power set of the reals. So that tells you there's a bunch of these sets. There's as many, in a cardinality sense, there's many of these Lebesgue measurable sets as there are sets of real numbers. There couldn't be any more than that because they are sets of real numbers. But a funny behavior about infinite sets, we can have two infinite sets of the same cardinality. Of course, that doesn't mean the sets are the same. There exist subsets of the real numbers which are not measurable. There exist non-measurable sets. In fact, an interesting question, I think, is how many non-measurable sets are there? Well, it turns out there's this many as well. There's as many non-measurable sets as there are measurable sets. You don't want to deal with those non-measurable sets. They're very, very exotic sets. Showing the existence of them requires the axiom of choice. The axiom of choice being a very reasonable thing to accept. But assuming the axiom of choice, we can construct, quote unquote, if you're familiar with the axiom of choice, construct is a almost ironic term to use, we know of the existence of non-Lebesgue measurable sets based on the axiom of choice. The construction of non-measurable sets is related to the, I have classified it as intuitively offensive Banach-Tarski paradox. Banach-Tarski paradox deals, if described in a physical way, with this most offensive idea. Very crudely put, it says I can take a sphere of radius 1, I can break it into 5 pieces, rigidly take those 5 pieces, glue 2 of them together and get a sphere of radius 1, and glue the other 3 together and get a sphere of radius 1. So you're taking a given volume and doubling it just by breaking the thing into pieces, and a small number of pieces. Those pieces are extremely exotic. What makes the Banach-Tarski paradox work from a measure theory perspective is those pieces are not measurable. So you're violating additivity. The measure of the parts doesn't equal the measure of the whole, in a sense. It's a violation of countable additivity is a way to interpret Banach-Tarski paradox. Interpreting it physically is not what this is about. This is not physical stuff. It's mathematical concepts, and some weird things can happen. And there's a link there to the Banach-Tarski paradox. It's a most amusing story. The appropriate place to tell it's in a measure theory class. A measure space, omega s mu, is said to be finite if the measure of omega itself is finite. We're requiring sigma algebra s to include omega. So mu is defined on omega. So if the measure of the whole space is finite, then we have a finite measure space. Something possibly useful if we were going to deal maybe with probabilities, where we'd want the measure of the entire space to be 1. We could maybe do some normalizing if we're in a finite measure space. Shifting gears a little bit with an eye towards integration. A simple function on measure space, omega s mu, is a measurable function in the sense defined above, which takes on only a finite number of values. So the range is just some finite number of y values, if you like. So this function must be constant on certain sets. Suppose the function takes on the value c1 through c sub n. Then there's a set of input values on which this function takes on the value c1. There's a set of input values on which this function takes on the value c sub 2, and so forth. If those sets happen to be intervals, then we're looking at something like a step function. The idea is those sets on which the function takes on, say, the value c1, that's going to be a measurable set. That set of values would be, treating s as the function, would be s inverse, the inverse image under s of c sub k. So that'd be the input values that produces the value c sub k. Will that set be measurable? Yeah, that's where the definition of measurable function comes in. So when we take these inverse images, provided s is a measurable function, and it is, provided s is a measurable function, each of these sets will be measurable. And let's linger on this for a little while. We're defining the integral of simple function s over omega to be integral over omega of s with respect to measure mu, d mu, as a sum from k equals 1 to n of c sub k, that's a function value, times a measure. It's the measure of the set on which the function assumes this value, c sub k. So this is awfully similar to Riemann sums. In Riemann sums, you get rectangles. They got a base and they got a height. The height's determined by the function value. There's your function value right there. The base for Riemann is determined by the length of an interval. Well, here the base is determined by the measure of a set, the set on which the function assumes the value c sub k. But these are very much similar to an idea of Riemann sums and those rectangles you get from Riemann sums. It's a base times height. There's the base, it's a measure of a set, and there's the height, it's a function value. Might say measure, sine height or absolute value of this is height. The function values could be negative and heights aren't negative. So I get a little stuck with that. I mean, that's a problem even with Riemann. But the fact that these C sub k's might be negative, height's not the right word to use. It's assigned height, given they could be negative. But that's the idea. It's a base times height thing. Well, a base times signed height thing. If I were to give these a name, I'd call them Lebesgue sums. Just like you have Riemann sums, which were sums of areas, well, signed areas of rectangles. Here we're getting something like a sum of signed areas of, Lebesgue rectangles. The only problem is the base isn't simply an interval, it's some complicated measurable set. But we can measure it, so that's how we'll weigh it, and think of it as base times height, signed height. Many more details available online in the Lebesgue setting, but that right there is the reason we took the definition we took for measurable function. And think of this kind of like Riemann sums, Lebesgue sums, and we defined a Riemann integral by taking limits of Riemann sums. Well, we're going to do the same kind of thing here. We're going to kind of treat these as Lebesgue sums, and in some sense, we'll take a limit of these to define Lebesgue integrals. As an example, consider this is a modified Dirichlet function. I got my reasons for dealing with it like this. Define d of x to be 1 if x is in the interval 0, 1 and irrational, and define d of x to be 0 if x is between 0 and 1 and rational. Strictly speaking, the regular old Dirichlet function interchanges the roles of 0 and 1. But I won't approach it like this because if we'll integrate over the interval 0, 1, so taking this to be the capital omega set, integrate this function with respect to Lebesgue measure, hey, it's a simple function, only takes on two values, 0 and 1. So we'll simply take 1 times the measure of the set on which the function takes those values, plus 0 times the measure on which the function takes on the value 0. It turns out, so there's your lack of rigor, that countable sets have Lebesgue measure 0. So the rational numbers between 0 and 1, actually a whole set of rational numbers for that matter, forms a set of measure 0. So we've got 0 from the function value, and we've got 0 from the measure of the corresponding set. Up here, we'll get a measure of 1. The measure of the interval 0, 1 is supposed to be its length. Measure generalizes the idea of length of an interval. So we'll have a measure of 1 for the whole interval. If we'll remove this set of measure 0, we should still have a set of measure 1. And we do, it follows from countable additivity. So the measure of this set is 1. The x values in the interval 0, 1, which are irrational, is a set of measure 1. So the integral is 1 times 1 plus 0 times 0. That's the reason the integral is 1. I bring this up for two reasons. It's a simple function. It's a little bit complicated, rational and irrational numbers. So Riemann can't do anything about this. Riemann can't evaluate this integral because this function's too discontinuous. We could use it as an example of a probability distribution. So we could say something like pick a number between 0 and 1 with a uniform distribution. Take a uniform probability distribution on the interval 0, 1. Pick a number at random. What's the probability that number is irrational? It'll be represented by integrating over the irrationals and produce 1 as well. The fact that we get 1 up here shows we really do have a candidate for a probability distribution. And the probability of choosing a number under this distribution between 0 and 1, the probability the number is rational is 0. The probability it's irrational is 1. The probability it's rational is 0. And that's not a complicated probability story, but it's one you can address with just Riemann integration. It actually takes the Lebesgue integration and the ideas of measures to deal with that. Okay, so we're building up Lebesgue integration. We're doing it in layers. So far, we've only defined the Lebesgue integral of a simple function. Now we're going to define the Lebesgue integral for a non-negative measurable function. For such a function, the Lebesgue integral over omega dm indicates Lebesgue measure there. We're defining it to be a supremum of the integral over omega of s, a simple function, dm, defined above. So these symbols are defined above. These are what I was calling the Lebesgue sums are. And we're taking s to be simple and s less than or equal to f. Well, if s is less than or equal to f, I expect all these Lebesgue sum things here to be less than or equal to the integral under f. Well, let's swell them up. Let's take a limit, and that's what the supremum does. So just as you define the Riemann integral of a function as a limit is the norm of the partition approaches 0, of Riemann sums, we're defining for this particular kind of function, the Lebesgue integral to be a limit of what I've called Lebesgue sums. So there's very similar behavior between what Riemann does and what Lebesgue does. Lebesgue's way deeper because measure theory has to be developed to do the Lebesgue stuff. But this should make some degree of sense. The functions are less than or equal to f. So I expect these integrals to be smaller than what I want this value to be. So we'll take a supremum over all such simple functions. That's what the sup's being taken over. And that's the definition of the integral of a non-negative measurable function. So we've defined Lebesgue integral for simple functions, for non-negative functions, always measurable. What's left is functions that are sometimes positive, sometimes negative, and that's to follow. Some properties so far. We need an idea of dealing with sets of measure 0 here. A set B in the sigma algebra of measurable sets such that the mu measure of B equals 0 is called a null set. A property which holds on all of capital omega except on a null set is said to hold almost everywhere, commonly denoted just AE. So the property might be property like continuity. Holds almost everywhere if it holds except on a set of measure 0. We ain't interested in sets of measure 0 in a conversation about Lebesgue integrals. Sets of measure 0 don't affect Lebesgue integrals. When we look at the LP spaces, and we're getting there, they're going to be based on this Lebesgue stuff. And this almost everywhere idea is going to play a big role when we look at the functions in the big LP spaces. Let's scroll back up to this Dirichlet function. You know what? This function was 1 except on the rational numbers. And we've claimed here the rational numbers have measure 0 because they're countable. Certainly worthy of a proof. We don't even have a formal definition of Lebesgue measure. But that's not a complicated result, but we'll leave it for real analysis 1. So this function is 1 except on a set of measure 0. So I could say this function, where it's understood that omega is the interval 0, 1, this function is 1 almost everywhere. That is, it equals 1 except on a set of measure 0, this set of measure 0 specifically. So there's an example of this almost everywhere idea. Some properties of Lebesgue integrals, a couple of which involve this almost everywhere stuff, is as follows. Suppose f and g are non-negative measurable functions on omega. Then the integral of f plus g is the integral of f plus the integral of g, additivity. Again, notice we're dealing with the largest class of functions for which we've defined the Lebesgue integral. We'll see some of these properties again because we'll have another class of functions for which we'll define the Lebesgue integral, those functions which are sometimes negative. For any alpha greater than or equal to 0, greater than or equal to 0, the integral of alpha f, if f is non-negative and alpha is non-negative, then alpha f is non-negative. So that's the reason the scalar has to be chosen to be non-negative. Claim is the integral of alpha f is alpha times the integral of f. These guys call it the scalar property. Property 1 and 2 together show us that Lebesgue integrals for this class of functions behaves in a linear way. An integral of a linear combination is a linear combination of the integrals. So something you see in Calculus 1, but for Riemann integration in Calculus 1. If f is less than or equal to g almost everywhere, then the integral of f is less than or equal to the integral of g, a property called monotonicity of the integral. There's also a monotonicity of measure as well, dealing with subsets and supersets. The integral of f equals 0 if and only if f equals 0 almost everywhere. Should make sense. Remember, we're dealing with non-negative functions here. I could certainly have, even in the Riemann setting, I could have an integral be 0 and the function not be the 0 function. Maybe it's positive sometimes, negative sometimes, and those cancel out when you evaluate the integral. But here we're dealing with non-negative functions. So this function is never negative. The only way the integral can be 0 is if the function's 0. Well, almost everywhere. You change this function f on a set of measure 0, that won't change the integral. That's why this almost everywhere stuff comes up. We're interested in integrals. Ultimately, we're interested in norms, and those norms are going to be defined using Lebesgue integrals. So that's where the almost everywhere thing will play its biggest role. If the integral of f is finite, then it must be that f is finite almost everywhere. Is finite is the best way to read this, which makes sense if the function were infinite and we've allowed these functions to be extended real value. I didn't make a big deal out of it, but it's been in the background even in these notes. If we allow this function to take on the value infinity on a set of positive measure, then you're going to get an infinite integral, the contrapositive of this. So there's some properties in this setting. We want to move a bit beyond non-negative measurable functions and look at general measurable functions. A class of result we will want is suggested by Fatu's lemma. The statement is, if f sub n is a sequence of non-negative measurable functions which converge pointwise almost everywhere to a function f, then f is measurable, first off. So a pointwise limit of measurable functions is measurable. That's what we extract from this, well, non-negative functions. And the integral of the limit function f is less than or equal to the lim_inf of the integrals of the f sub n's. Fatu's lemma, we can see specific examples where this is a strict inequality. What we really want to do is get an equality and deal with a regular old limit, not a lim_inf. Without more hypotheses, you can't. So we really want a convergence theorem. Fatu's lemma is not a convergence theorem because it deals with lim_infs, and we've got an inequality here. It's the monotone convergence theorem that deals with non-negative measurable functions. So similar to Fatu's lemma, we've got a sequence of measurable functions converging pointwise almost everywhere to a function f. Same thing we had up here. Here's a new hypothesis. And f sub n is less than or equal to f sub n plus 1 almost everywhere for all indices. That is, for a given x value, you could also read this f sub n of x is less than or equal to f sub n plus 1 of x for almost all x in the appropriate set, capital omega, I guess. But what's happening is if I fix an individual x value and look at the corresponding function values, it's a monotone increasing sequence. So this monotone increasingness is what, in some sense, allows us to deal with this inequality in this lim inf. And the conclusion we can draw is the integral of f, that is the integral of the limit of the f sub n's, right? The f sub n's converge to f, point-wise almost everywhere, but f equals the limit of the f sub n's almost everywhere. So this is really just a substitution and some details about the almost everywhere stuff. And this is the claim. This equals the limit of the integral of the f sub n's. So we're bringing this limit outside of that integral. When can you do that? The answer is when you have a convergence theorem that says you can do that. In the setting of non-negative functions, that convergence theorem is the monotone convergence theorem. So we need this type of monotonicity to bring limits outside of functions. Does Riemann ever talk about this kind of thing? And why would you want to do this kind of thing? Yeah, Riemann talks about it. Riemann requires uniform convergence of a sequence of Riemann integrable functions. And if you've got that uniform convergence, then you can take limits in and out of an integral, as is done here in the Riemann setting. Uniform convergence is way more restrictive than all of this stuff that we're addressing. Secondly, why would you want to do this? Well, think how hard it is to integrate stuff. Look at e to the negative x squared. It's a bell curve, right? It's a normal distribution. It's not quite normalized. I need some means and standard deviations and some normalizing factors. But to integrate the normal distribution is basically to integrate e to the negative x squared. And you don't know how to integrate e to the negative x squared using those techniques of integration from Calculus 2. But you can take that e to the negative x squared and find a power series for it. And power series are limits. So you can take that e to the negative x squared function and write it as a power series. The convergence is uniform. This is a Riemann setting discussion for this part. You can bring the limit outside. Then you need to end up integrating powers of x. Power series involve powers of x. And that's easy. So you've taken something you have no clue how to integrate, e to the negative x squared, and turned it into a bunch of integrals of powers of x, which are really easy to integrate. Oh, you paid a small price for that. You picked up a limit, and you're getting the answer in terms of a series, but you couldn't do it otherwise. So 2 observations. First, this is better than Riemann. And secondly, there's reasons for wanting to bring limits outside of integrals, real pragmatic reasons like simply evaluating integrals. So let's look at our last category of functions for which we'll define the Lebesgue integral. For a general real-valued measurable function f, so no constraints about non-negativity, define the positive and negative parts as f superplus of t is the maximum of f of t and 0. So if f of t is positive, this is the maximum, and we get that out as f plus of t. If f of t is negative, then this is the maximum, and we get 0 out. So what this does is f plus of t takes a function f of t and sort of chops it off along the x-axis, t-axis, I guess, in this case. And it just wipes out the bottom part and makes it 0. Negative part takes the negative minimum of f of t and 0. So if f of t is negative, this is the minimum, but then it throws a negative sign in that. If f of t is positive, then this is the minimum. So geometrically, what this one does, if we have a non-negative function and we look at this, it just squashes all the positive stuff down to the t-axis. So you lose all the positive stuff, and it keeps all the negative behavior of the function. But then the negative sign turns all that over. So it revolves it about the t-axis, if you like. So that the positive part contains information about the positive part of f. The negative part contains information about the negative part of f of t, very literally, but doesn't equal the negative part because of that negative sign there. So we've gone out of our way to make the positive part non-negative, and the negative part, this is weird, is also non-negative. So both of these are non-negative. If we were to write f itself, the original function, we could write it as the positive part minus the negative part. So we get a difference in there. Why would you want to call the negative part something that's non-negative? Because we're trying to define the Lebesgue integral here. And we have the Lebesgue integral from our past, last 4 pages of notes, defined for non-negative functions. So that's the reason we want to express positive and negative parts both as non-negative functions, because we know how to integrate non-negative functions. We define those in terms of integrals of simple functions. If the integral of the positive part is finite and the integral of the negative part is finite, and integrals can be infinite even in the Riemann setting, so we're imposing a finiteness on these parts, then we'll define the integral of function f, an arbitrary measurable function, as integral over omega of f is the integral of the positive part minus the integral of the negative part, which makes pretty good sense because f equals the positive part minus the negative part, Well, what's up with this constraint on finiteness here? Well, without that, we potentially get an infinity minus infinity indeterminate form. So that's the reason we're making that constraint to have this definition. And that's our final definition of integral, or Lebesgue integral, if you like, all of this being done with respect to Lebesgue measure in practice. Oh, I take it back. We'll mention this complex version, though I don't know if we'll ever use it. We're primarily going to consider functions of real variables and real outputs, but we could also take a function of a real variable input and a complex output and consider the real part of the output and the imaginary part of the output, provided we get infinities on the integrals of the real and imaginary parts, both of which are real, by the way. The imaginary part of a complex number is itself real, kind of like that non-negative stuff that we were talking about. But we could integrate both of those parts and simply add them together and reintroduce the identity, kind of like we reintroduced the negative sign upstairs. So, well, that's our last Lebesgue integral definition, and this is something we're likely to not touch on much anymore, though the Lebesgue stuff is central. Okay, so we got a new family of functions that we can Lebesgue integrate. Let's check some properties of integrals for that class of functions, general measurable functions, we called them. And if indeed, as above, you get additivity. The integral of the sum is the sum of the integrals. For scalars coming from the field, be they real or complex, that's the fields we'll deal with. The integral of alpha f is alpha integral of f. Again, combining these two properties in this class of functions, we get the linearity behavior of an integral as usual, and we get the monotonicity to hold. If f is less than or equal to g almost everywhere, then the integral of f is less than or equal to the integral of g. Quick observation, didn't we just do this? No. Let's scroll back up, because we stated those three properties before, but the setting was different. Up here, we were considering non-negative measurable functions when we stated those three properties. Down here, we're considering general measurable functions as defined above. So it's a different class of functions. So a different result. All right, now we're going to shift gears and talk about stuff in the title of the section, talk about the LP spaces. So when we're taking integrals, you probably want to be thinking Lebesgue integrals, though these are done and spelled out in terms of measure spaces. So it could be something a touch more abstract. The next several results are covered probably in Analysis 2. Chapter 7, the LP spaces, completeness and approximation. So linked to some notes there. In which case, the classical Banach spaces are covered. The LP spaces based on real numbers. And you use all that Lebesgue measure stuff. They can be covered in a more general setting, general LP spaces, in which case we consider LP spaces over measure spaces, which is the approach we're taking here in terms of the definitions. Okay, this is going to look a little unusual. We're interested in the capital LP spaces, the big LP. We're using a different font here because we're talking about a different space here. First, the definition for omega s mu, a measure space, and p greater than or equal to 1, define the LP norm. Okay, if I'm going to call it a norm, I need to make sure it's a norm. We'll take care of that here in a little while. So let me just go ahead and verbally read this as the LP norm of f is defined to be the integral over omega, absolute value of f to the p power, integrated 1 over p, pth root of. So you're raising to the pth power here, and you're taking a pth root on the outside. Why you would want to do that? Not immediately clear. I'll try to put some inspiration on it before we're done here. And we're going to let calligraphy LP of omega s mu be the set of all functions f mapping omega into the field, real or complex, such that f is measurable and this quantity, the LP norm, is finite. So it's a collection of all vectors. We're about to show it's a linear space. So I'm legitimate in calling these functions vectors. So big transition here where we're talking about normed linear spaces, a little bit more hands-on with an idea of vectors being functions. They're these kinds of functions. This collection of functions is called the calligraphy LP space on omega. We're not interested in the calligraphy LP space. We're interested in something slightly different. I'll hang with that clunky verbiage of calligraphy LP. So for now, this is simply a set of functions mapping omega into the scalar field for which this integral is finite. Integrals can be finite or infinite. Throw out those functions that produce an integral of this sort, which is infinite. Keep those that produce a finite value for the integral. Loads of details omitted here. This kind of thing you'd cover in real analysis 2 probably. Proposition 2.35 says calligraphy LP is a linear space. So quite a claim, really. You're telling me if you got a function f and this integral is finite, and you got a function g and this integral is finite, the integral of f plus g also finite? Apparently so. But that's not immediately obvious, I don't think. Because this is such a weird deal with the absolute values and the pth power. I mean, p is not even an integer. It's just a real number greater than or equal to 1. On top of that, you take a pth root. So there's a good deal of stuff to be established simply to show that this is a linear space, that we've got closure under linear combinations, for example. Take the real analysis sequence. In part 2, you'll take care of that. So we'll take that as given, that calligraphy LP really is a linear space. The following for our interest is somewhat peripheral. It's called Hölder's inequality. It says for all measurable functions f and g, with f in calligraphy LP and g in calligraphy LQ, where 1 over p plus 1 over q equal 1, we have the product fg in calligraphy L1, and we got the L1 norm of f times g less than or equal to the LP norm of F times the LQ norm of G. Okay. If we were face to face, I'd ask you, does that remind you of anything from sophomore linear algebra? Fingers crossed you'd chime in. Oh, that's just a Cauchy-Schwarz inequality, isn't it? Well, it looks a little like the Cauchy-Schwarz inequality. It's a little weirdly messed up because we got LP norms and LQ norms and an L1 norm. But think of Hölder's inequality as playing a role similar to the Cauchy-Schwarz inequality or the Cauchy inequality from sophomore linear algebra. What'd you use the Cauchy-Schwarz inequality to prove in linear algebra? You proved the triangle inequality for norms of vectors using the Cauchy-Schwarz inequality. That's the role Hölder's inequality plays. Details omitted, but this is playing the role of the Cauchy-Schwarz inequality in establishing the triangle inequality. And here we're calling the triangle inequality Minkowski's inequality. It says for all measurable functions f and g in LP, p greater than or equal to 1, we have the LP norm of f plus g less than or equal to the LP norm of f plus the LP norm of g. That is, the LP norm satisfies a triangle inequality. If you buy that, then you should buy that the LP norm really is a norm. The hard part is establishing the Minkowski inequality. Very quick comment in passing. This is Hermann Minkowski, was one of Einstein's instructors. Wasn't impressed with Einstein as a student, called him a lazy dog at one point. But after Einstein publishes Special Relativity in 1905, Minkowski, quite impressed, said he didn't think Einstein had it in him. But Einstein publishes Special Relativity as a very physicsy idea, and Minkowski gets a hold of it and sort of encapsulates it in a more vector spacey setting, sometimes called Minkowski spacetime. So that's the Minkowski in Minkowski's inequality, just FYI. A mathematician, but with some physics background also. So in Calligraphy LP, the LP norm satisfies a triangle inequality. It really is a norm. Funny story. We ain't here to look at Calligraphy LP. Remember how we introduced almost everywhere? We don't care about functions that differ almost everywhere. They're going to have the same norms. They're going to behave almost everywhere the same as a function that's equal to them almost everywhere. Leading us to define the following. For p greater than or equal to 1, let capital N be all f in Calligraphy LP that has norm 0. So this must be functions which are 0 almost everywhere. If you'll look back at the definition of the norm in terms of an integral of absolute values, the only way you're going to get 0 out of those integrals is if this function equals 0 almost everywhere. That's an alternative way to state this. And they've stated in terms of the LP norm because we're taking specifically a function from Calligraphy LP. But these are functions that are equal to 0 almost everywhere. Define capital LP, notice the difference in the fonts, that's intentional, capital LP of omega S mu, let this denote the quotient space. Whoops, here is a typo. This should be Calligraphy L. Calligraphy LP mod N. And this is what we'll call the LP space on omega. So taking a quotient of Calligraphy LP with this collection of vectors that are 0 almost everywhere, functions that are 0 almost everywhere. Remember, quotient spaces can be interpreted in terms of equivalence classes. And what we're getting out of all of this is an involved way simply to say two functions are in the same equivalence class in the quotient space if they're equal almost everywhere. So if F equals G almost everywhere, in this quotient space, we don't distinguish between F and P. They're both from the same equivalence class. In fact, an alternate way to develop the LP spaces and the way it's done in the Royden and Fitzpatrick book we use in the real analysis sequence is to take the calligraphy LP and partition it into equivalence classes. We're exactly that. We say two functions are equivalent if they're equal almost everywhere. And then LP is defined on equivalence classes of functions. So that's effectively what we've done with this. But you start with the equivalence idea in real analysis, likely. Here we've got it out of quotient space, which leads to an equivalence class interpretation. So in the end, we're in the same place. Okay, we've seen that the norm, the LP norm, is a norm on LP, and simply it's the same norm we have on calligraphy LP. And we'll see that LP is complete. Big LP is complete. So we got a complete normed linear space. Then we got ourselves a Banach space. So the LP spaces are examples of Banach spaces. All right, so we've talked about LP spaces for P greater than or equal to 1, the odd thing to say, and strictly less than infinity. What we're about to do is extend these ideas to L infinity. So we need to define that. We'll do so by first defining an essential supremum, F, on measure space, since we've had omega, S, mu. The essential supremum of F is defined as the infimum of R, such that the absolute value of f of x is less than or equal to R almost everywhere on omega. So these are functions that are essentially bounded. That is, you get to throw away a set of measure 0. And then if you can get a bounded function, you've got a function that's essentially bounded. It could do some wild stuff on that set of measure 0, but as we've seen, I don't care what happens on sets of measure 0. Norms are going to absorb all that stuff. Integrals are going to absorb all that stuff. Norms are defined in terms of integrals. So it means what it says, but the idea is it's an upper bound on the absolute value of f of x after you throw away sets of measure 0. It's essentially an upper bound, essentially at least upper bound. And such functions are called essentially bounded, provided that essential supremum is finite. Let calligraphy L infinity denote the set of all essentially bounded functions on infinity. Define big L infinity of calligraphy L infinity mod n, where n was defined as above, functions which have an essential supremum of 0. And that introduces yet another space, L infinity. And guess what? L infinity is a norm linear space under the essential supremum. There's a limit relationship between the LP norms and the L infinity norm, it turns out. So we've got normed linear spaces, and in fact, those are complete as well. As the Rees-Fisher theorem states, for P between 1 and infinity, including infinity, since we've defined the L infinity spaces now, LP is a complete norm linear space normed by the LP norm. Kind of have to deal with the L infinity separately, but that too is a complete normed linear space. In other words, the LP spaces are examples of Banach spaces. And examples, just to overlap with the previous section a little bit, these are examples of infinite dimensional normed linear spaces. So exotic things can happen in these Banach spaces. So that takes care of an introduction of the big LP spaces. Somewhat complicated. It requires all that integration theory and measure theory. Something that's a little more tangible, hopefully, is the little LP spaces. These we'd cover in Analysis 2. They're mentioned in Chapter 7 of the Royden and Fitzpatrick book. But you know what? Even those guys, they shove them in the exercises. So they're mentioned, I don't know if they're mentioned at all in the body of the book, but they play a big role in the exercises. And these are sometimes called sequence spaces, whereas the big LP spaces are called function spaces because the vectors are functions. These are also examples of complete normed linear spaces, but what we have here are sequences of real numbers or complex numbers. So define little LP for P greater than or equal to 1, but finite, as LP is a set of all sequences, x1, x2, blah, 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 such that the entries in that sequence come from the field, the reals are the complex numbers, and the sum from 1 to infinity of the absolute value of x sub k to the p power is finite. You want to define a norm? Well, we'll take that sum from 1 to infinity of x, absolute value of x sub k to the p power, and take a pth root of it. You know, that's the same kind of thing we did in the big LP spaces, except we had integrals instead of sums. Yeah, integrals and sums are somehow intimately related. Integrals are limits of sums. So what we're taking here ultimately then, when I look at this is a way we're going to define the little LP norm. LP consists of all sequences of real numbers or complex numbers, which have finite LP norms. And that's pretty much what we did upstairs when we looked at big LP. Well, when we started with Calligraphy LP. So we've got a norm. Apparently, it's a norm. Details to be shown on that as well. And I promised to try to make some sense out of those crazy integrals. So let's try that on for size now. Suppose p equals 2. If p equals 2, I wouldn't need those absolute values, not if these are real numbers. We'd have the sum from 1 to infinity of x sub k squared, square root of. Dude, that's just totally Rn style. That's very much like the Euclidean norm that you're used to. Well, except for the infinity thing on the top. So this, when p equals 2, reminds me very much of regular old vector spaces from sophomore linear algebra, except for the infinity thing, when p equals 2. Well, it turns out when p is greater than or equal to 1, we also get a thing that determines a norm. If instead of sums, we took integrals, let's run back and look one more time, the LP norm definition. There it is. Same thing. Absolute value to the p power, pth root of. Except instead of a sum, where we had sequences, we've got an integral, where we've got functions. So very similar behavior, and just trying to make this look a little less bizarre and out of the blue that they would choose something like this to define a norm. Take your inspiration from Rn. We'd sum squares and take a square root. And when p equals 2, there's rather similar things going on here, except it's an integral instead of a sum. And it turns out for p greater than or equal to 1, these manipulations define norms. The LP spaces are complete norm linear spaces for p between 1 and infinity, including infinity. What we'll do for the L infinity, because I glossed over that, we'll simply take as the L infinity norm the least upper bound of the set of absolute values. So that'll be the norm. L infinity will consist of all sequences that are bounded in that sense. So least upper bound of the set of absolute values of the terms in the sequence, bounded sequences, are what's in L infinity. And the norm of a sequence is that least upper bound of the absolute values. These are complete norm linear spaces. So the little LP spaces, they're also Banach spaces. Don't have to go into all that measure theory stuff to talk about the little LP spaces. Potentially you could address the LP spaces in a senior level class because it doesn't require all that measure theory stuff. A normed linear space is said to be separable if it contains a countable dense set. Okay, we're going to look at some supplemental material that talks more about this. We're not terribly interested so much hands-on with a countable dense subset, kind of got my eye on the bases. We're talking norm linear spaces. I like to talk about bases. And this separability, at least in the Hilbert space setting, is very intimately related with the existence of a basis. I want a nice orthonormal basis like Rn has. Well, you'll get it in Hilbert spaces, you'll get it. But separability comes in with this definition, a countable dense subset. Okay, the real numbers form a one-dimensional separable normed linear space because the rational numbers are countable and they're a dense subset. Claim here is L infinity is not separable, proposition 2.42, but LP, little LP, is separable for all other admissible values of P, for P between 1 and infinity, excluding infinity. Idea of a proof on this little theorem here, so we can talk proofs, but I think I can talk you through this. Elements of the little LP spaces are sequences with some kind of boundedness. Sum the absolute values to the P power, you get something finite. I'll give you a countable subset of that. Let's take the set of all sequences consisting of a finite number of rational real numbers or rational complex numbers, if the field is the complex numbers. Sometimes they're called Gaussian. Maybe that's Gaussian integers. But take a rational plus I times another rational. That's what I mean by rational complex number. By taking a sequence with finitely many of those and all the other entries being 0, that gives you a countable set, and that gives you a dense subset. What this is a rip-off of the fact that the rationals are countable in the reals. So here we've got an infinite tuple, kind of like an infinite dimensional vector. It is an infinite dimensional vector. And we're using rational numbers to create a countable dense subset. So the countability part is the part where we have to require a finite number of rational numbers. If I take all sequences of rational numbers, that's not countable, so I can't use that. So we got to be a little careful with accountability, and the denseness with these rational numbers follows just like it does in the real numbers. So there's a whole bunch of stuff. An introduction to LP spaces, and a bunch of introduction to Lebesgue measure and Lebesgue integration. What we'll do next is look into I think products of normed linear spaces comes next, and we'll look shortly at a supplement from a different source that goes through and tries to make this stuff more geometric. Like me some geometry. So the more geometric we can make it, the better. And we can make it its most geometric when we look at Hilbert spaces, not Banach spaces. Hilbert spaces have inner products, so you can talk about angles between vectors in Hilbert spaces, and they'll behave just like they do in Rn. So that makes them something you can almost visualize. So I will see you soon. We're nearing the end of chapter 2. I'll see you in section 210 next time. Have a nice day.